Okay, thanks, and thanks for coming, and please don't hesitate to stop me whenever something does not make sense, to ask questions. So I'll talk about graphs, vectors, and integers, and as the title suggests, this will be a combination of combinatorics and some geometry and some number theory. Okay. And let me start with the main, so I see that you're hesitating if, okay, so I should say the right things at the beginning, but that's okay, yeah, that's okay, all right, yeah, you're right. Okay.
Interesting collection of stories.
Okay, good. So the main combinatorial object I'll consider is what's called the Cayley Sum Graphs. So probably many of you have seen the definition, but let me go over it. I'll have a billion groups. They will be finite always. So we have an abelian group, and we have a set S, which is a subset of the group. And I'll call it usually as a set of generators, although sometimes they will not generate, maybe. So this is just a name, it's just a subset. And then the Cayley Sum Graph of the group H with respect to this subset S is a graph, finite graph, whose set of vertices are the set of all elements of H. And two of them, A and B, are adjacent if and only if their sum belongs to S. Right? So that's very simple. So this will be a abelian group, and it's I use additive notation. And here is one example. So you take the cyclic group with 8 elements, Z8, and the set of generators here is 1 and 3. And you see that 2 are joined here if and only if their sum is either 0 or 3. So 7 is joined to 4 because the sum is 11, which is 3 modulo 8. Okay, so this is an example of a Cayley sum graph, and I'll use 2 simple facts about them. So the first fact is that each Cayley sum graph is regular, namely the number of edges incident with every vertex is the same, and the degree of regularity is exactly the cardinality of the set S, right? Because if we think about some A, then it's connected to every B, so that A plus B is an element of this generating set. So for every choice of the element of the generating set, we get one B. And you see that we can have loops. Maybe someone was about to ask it, I think. Doron, yeah, okay. So we may have one loop at each vertex, right? If 2A is in our generating set S, then A will be connected to itself. And if we have a loop, we think about it as contributing only 1 to the degree. So because sometimes this is counted as 2, here it's good to count it as 1. So this is so maybe there are loops, but if there are loops, there is only one, at most one loop in each vertex. And then the second fact, which is also quite simple, is that we have an expression, a simple expression for the eigenvalues of these graphs. So for a graph, we have the JC matrix. It's a matrix whose rows and columns are indexed by the vertices of the graph. And in place UV, we have 1 if and only if U and V are connected. So that's a symmetric matrix. It has real eigenvalues with orthogonal eigenvectors. And the eigenvalues here are given exactly. So you take a character of the group, and you take the sum of the character over all these generators, elements of S. You take the absolute value of it, and then it will be plus or minus Z. And this is just because the eigenvectors are the characters themselves. They are eigenvectors of the square of the matrix. This is because it's a Cayley sum graph. If it's just a Cayley graph and not a Cayley sum graph, then the expression is the same thing without the absolute value, and basically for the same reason. Okay. So we know the eigenvalues, and the main theme would be what we'll try to do is to use some relations between the spectral properties of graphs and their structural properties. So there are many results like these. And then we can combine them with some character sum estimates that will enable us to estimate the eigenvalues of our graphs to deduce or to get some insight about structure of Cayley Sum Graphs. And this will have examples. I'll try to show you several examples. I think it's here. So I wrote that it's useful in the study of problems in extremal graph theory, in additive number theory, and in geometry and information theory. And I'll show one geometric example and maybe two which is motivated with something from information theory, and two examples that are more number theoretic. This is okay. And the first one is this geometric example. So consider the following problem. It's a kind of an extremal problem in Euclidean geometry, if you want. I denote by f of n. So this will be the maximum possible value of the norm of a sum of n unit vectors. So we are in Euclidean space. We take n vectors, each of them of unit length, and we want the sum of them to be as large as possible in norm. So we want that all of them would kind of point in the same direction, but they are nearly orthogonal in the sense that among any three of them, in this example, some two are orthogonal, right? So if among any two of them, two were orthogonal, namely if they are pairwise orthogonal, then just n orthogonal unit vectors, and then the norm of the sum is square root n. And the question is, can it be much bigger, or how big can it be if they are nearly orthogonal in the sense that is written here? And this was a question suggested by Lovas. So we want to estimate or to determine this f of n. So I often say in talks that a normal lecture is divided into three parts. So the first part is the introduction, when you talk about what you are going to talk about. And then the second part is like the main part of the talk, and this is when you talk about these things that you are talking about. And then the third part is a summary, and this is when you talk about what you talked about, right? But sometimes there is this fourth part, and this is when you talk about what you are not talking about. So let me talk a little bit about what I'm not talking about, which is just to say something about the motivation of this, just to say the relevant buzzwords for those who know the notion. So some of the motivation of Lovas for asking this question comes from information theory. So what we want is to estimate the maximum possible what's called Shannon capacity of a graph in which the independence number is 2. Okay, so this tells us something about the maximum zero error capacity of a noisy channel if the channel is such that when we use only messages that are very short of one letter, then we can use only two distinct messages. But if we use long, then maybe the effective size of the alphabet gets bigger. So this is the Shannon capacity. Again, I'm not really talking about it. And it's not even known for that question about the Shannon capacity if this capacity tends to infinity with n, the size of the graph. So, or is it bounded maybe by 5 or something, as far as we know. And one way to think about it is to try to estimate the maximum possible value of what is called the Lovas theta function of such a graph, because the Lovas theta function is some geometrically defined quantity that gives an upper bound for the Shannon capacity. So it's kind of a related question to the maximum possible Shannon capacity, and it's essentially equivalent to the questions that I mentioned. Although it's not exactly the same f of n, there is some translation between one and another. Yeah. So it will. Here it will, for this question it will tend to infinity, and actually, and also right. So the theta function also tends to infinity. It behaves like n to the 1/3 here, although this will not. Okay. But anyway, so it's just to say that there was some motivation for that, and here is what is known about it. So the trivial bound for this f of n is that it is at most n, because by the triangle inequality, right, it's the sum of n unit vectors, is least square root n. In fact, you can do a bit better because you could take n pairwise orthogonal vectors. You could take also, if you want, two sets of pairwise orthogonal vectors, each of size n over 2. This would still have the properties that among any three, some 2 are orthogonal. And you can make sure that there's some point in the same direction. This will give you square root 2 times square root n. So it will improve by a little bit. But in fact, the truth is more like n to the 2/3. So it was shown by Konyagin. That's a clever argument, short, simple argument, that f of n is not more than some constant n to the 2/3. And then there is another lower bound that's more difficult by Cushing and Konyagin. That's a probabilistic lower bound that uses something and shows that f of n is at least some other constant n to the 2/3 over log n. Okay. And I want to tell you something about, so I could show that f of n is in fact up to a constant. The truth is n to the 2/3. So it's between maybe 1 over 5 n to the 2/3 and 3 times n to the 2/3. Uh-huh. Yeah, I mean that for every n, and I mean that there exists some absolute constant, so that, and I know that I once, long ago, I had some paper, so I had some long discussion with Schinzel, because he was the editor, and so this was a paper in number theory, but I used this notation of omega and O, and he didn't understand what's written there, and we had like really long conversation about what it means, this omega, and what. But okay, so omega means that there exists an absolute constant c, so that for every n, f of n. Yeah, yeah, you could right. So some people use also equal to big O, and it's. But as long as you all understand what I mean by this, then it's okay. But this is. But still, Peter, don't be ashamed to ask questions whenever. I don't want you to. Okay. Yeah. You warned me. So that's it. Okay. And I want to tell you something about the lower bound here, because this is where the Cayley Sum Graphs appear. So about this construction. So there is this construction, and it's a construction of some Cayley Sum Graph. And I wrote here the construction just that you see that it's simple to describe, but doesn't really matter. So it's. Yeah, but once you know it for infinitely many n, it's easy to get it for yeah, you could fill the gaps. Yeah. Yeah, because just think what this question means. It is easy to see, but okay. So I'll do it only for powers of 8, if you want. But that's enough. So let's take an elementary abelian group of so just vectors of length 3k, binary vectors with addition modulo 2, and I describe here the generating set, so you have to view these things as elements of the finite field with 2 to the k elements. It's not so important, but there is some specific way to define it. And this graph has 2 to the 3k vertices, so just all the binary vectors of length 3k. And it is regular of degree, the cardinality of this set S, which is here roughly a quarter n to the 2/3. Right? So 2 to the k minus 1 times 2 to the k minus 1 minus 1. Okay. And then it turns out that this graph, because of the definition, you could show that it has 2 properties. So by properties of some error correcting codes that are called BCH codes, and that's a simple thing to show, this graph is triangle free, doesn't contain any triangle. Okay, so let's believe that. And then by Carli-Tsuchiyama bound, which is some bound for character sums, it's basically a special case of Weil theorem. So it says that the smallest eigenvalue, you see, this graph has no loops, because here actually we are over a group where the order of every element is 2, so we don't have yeah, I guess besides 0, let me not take 0. never mind. Okay. So the trace here is 0 because there are no loops, and that means that the sum of the eigenvalues is 0. So the smallest eigenvalue is negative, and the question is how negative can it be? And to know that it cannot be very negative, we just have to bound the absolute value of this character sum that gives a. And this Cayley-Sum bound tells us that it's not very negative. So in absolute value, it's not more than 2 to the k, which is, well, minus 9 times 2 to the k. So the absolute value is at most 9 times n to the 1/3, somewhat small. Okay? And now from this, we want to get these vectors that are nearly orthogonal and their sum is big. So here is how we do these. So let's take the adjacency matrix of the graph. Again, rows and columns indexed by vertices. In place uv, you have 1 if and only if u and v are adjacent. So this is A. And now you take lambda, that's the absolute value of the most negative eigenvalue, and you add lambda I. So that makes this matrix positive semi-definite, because now all the eigenvalues became. And we divide by lambda to have 1s in the diagonal. So now we have 1s in the diagonal, and we have 1 over lambda everywhere where we had an edge before. So this is positive semi-definite, and because of this, it is the Gram matrix of some other. So we can take a square root, and the rows of the matrix that is square root, these are vectors. Now you see, because the graph is triangle-free, whenever we have 3 vectors, then if we look at the corresponding places in the matrix, at least in one place we see 0, because there is no triangle. So it means that 2 of these vectors are orthogonal. So this is good. And on the other hand, the sum is big because the quantity is the sum of vi norm square. This is just the sums of all the products ui, vi times vj. So it's just the sum of all entries of this matrix. But we know what it is, right? In the diagonal we have 1, so this is n. And in nd places, d is the degree of regularity, we have 1 over lambda. So altogether the sum is this. D was n to the 2/3 up to constant, so this is a, yeah, you see that here it's written equals omega instead of bigger or equal. It means the same, okay. So this is lambda was n to the 1/3 up to constant, d was n to the 2/3, and this gives the bound. Okay. So this was a geometric example, and I'll show you 2 other examples that are more number theoretic or additive number theory. So the first one has to do with sum sets. Okay? So I wrote here what it means, a sum set in any abelian group, or if you want, in a cyclic group of p elements, but in any abelian group. So we just take a set A, capital A, and then you look at all the sums of little a plus little a prime, where a and a prime belong to capital A. So this is a sum set. And sum sets really play a major role in this additive number theory. I checked yesterday, so they are in Messinet 182 papers in which the word sum set appears in the title. And there are actually 54 more papers in which the word sum set also appears in the title, but as 2 separated words with a hyphen between them. So really there are lots. There is at least 1 book in which sum set appears in the title. So somehow it looks interesting to understand which sets are sum sets, even over the integers. But we want to look at a cyclic group of prime order. So just, and I think, so I don't know to show it, but I suppose that it's a computational problem, given a subset of ZP, decide if it's a sum set or not. That looks hard. So I would guess it's NP hard. I don't know if it's thought about it yesterday, but yeah, maybe it's hard. Okay, now you could ask, and people ask, how many subsets of ZP are sum sets, and Green and Ruja showed that it's roughly 2 to the p over 3, so there are many of them. And let me show you, here are some examples of sum sets in ZP, and that should lead us to think that something may be true. So see, ZP, all of it is a sum set because it's ZP plus ZP. It's also A plus A for many other A's. Whenever you will take a random A with a little bit more than square root p elements, then its sum with itself will give you everything. Okay? Now, it's also true that for P at least 7, if you omit any single element from ZP, that's also a sum set. And here, actually, it was written what this sum set is. But when I looked at it this morning, it seemed to me that it's wrong. So I erased it. But definitely, it's true that every subset, if you omit one element, then it's not difficult to write an expression. And here is also an argument that for every P at least 3, let's say, if you delete 2 elements, then it's a sum set. Because if you delete 0 and 1, then it is A plus A just for A, which is 1, 2, up to P minus 1 over 2. And any set of 2 elements is the affine image of this 0 and 1. And it's easy to see that the affine image of a sum set is a sum set. Because you can... OK, so everything is a sum set. Everything minus 1 element is a sum set. Everything minus 2 elements is a sum set. Maybe also everything minus 3, and so on. And indeed, this was first proved by Green in his thesis, actually, that let us denote by f of p the maximum f, so that whenever we take the complement of f elements in ZP, so we take ZP, we throw only a small number of elements, f of p, then whenever we throw only this small number of elements, then this is a sum set. So maybe, yeah, I'm not sure if it's reasonable to think that it should be true, that if we didn't throw too many, then it's sum set, but this is what he showed. So he showed that if we throw less than some constant log base 2 of p, then it's always a sum set. And with Gowers, they showed an upper bound that you could throw something like p to the 2/3 times some log factor and get something that is not a sum set. So the natural question, Green asked it, is what is the true behavior? So I know somewhat better, but still it would be nice to understand what's really going on. I should say, by the way, that in all the 3 examples that I'll talk about, we still don't really understand what's going on. So I'll mention at the end, this will be after you leave, so I'll mention the problems. I'm not, but, so I'll mention what is left. But one problem, so here, this f of p indeed behaves like a power. So it's at least square root p over square root log p up to constant, and most p to the 2/3 over some log to the 1/3 p. But the truth, I think, should be, if I have to conjecture, it should be the lower part. So it should be closer to square root p. There are some reasons to think why this should be true. But and because I think that this should be true, I want to tell you about the upper bound, because this is what should be improved if we believe that. So again, there are some Cayley Sum Graphs there. So here is, again, I'll not really describe the proof, but it's kind of a plane of proof, so it's kind of an outline. So to prove the upper bound, we have to show that there exists a subset of ZP of size at most constant. Here I wrote 16, just to have some explicit constant. P to the 2/3 over log to the 1/3 p, so that if we omit all these elements, then what we get is not a sum set. Okay. Now, how are we going to do this? So we are going to decide about the set of elements that we are throwing in 2 steps. So it will be the union of f prime and f double prime, and each of them will be of size, say, 8 times p to the 2/3, so half of them. Okay. So first I choose f prime. I later say that I choose it randomly, but it doesn't matter. Let's choose f prime first. Now, once I chose f prime, I still didn't choose f double prime. But if I want now the complement of f, which will contain f prime, to be a sum set, a plus a, then this a. Yeah, so I want something with small, you'll see soon, something with small Fourier coefficients, and but it's but yeah, maybe there is, but anyway, so the best way I know to do it is to choose f prime randomly, but let's now just choose some f prime. So if the complement of f, which will contain f prime, has to be a sum set a plus a, then it means, if you think about it, that a has to be an independent set in the Cayley sum graph of ZP with respect to f prime, because every sum of 2 elements of A cannot be an element of f prime. That exactly means that it's an independent set. So So then we know the eigenvalues of G are these character sums, so we have this expression for them. And if we know that this exponential sum is small, right, so if we know that it is small enough, and in particular for random f prime, it's easy to show that it's small by any large deviation inequality you would want. So if they are small in absolute value, all of them, then you could show that such a graph does not have too many independent sets. In fact, one thing that you could do is use, since anyway I didn't write here any quantitative estimates, you could use some old estimate of Hoffman that says that the maximum independent set, you use it in your paper, right? So that's the maximum independent set. Yeah, but that's okay. So that the maximum independent set in such a graph is small, and just the number of small sets is not too large. So if the maximum is small, there aren't too many of them. But in fact, one can show a somewhat better estimate. It's a number of independent sets is small because such graphs are strong expanders, so somehow it makes sense. Okay. And now you see, all these independent sets are candidates to be sum sets. But now we still are allowed to choose f double prime. And f double prime, there are many choices to choose it. And still, the complement of f prime union f double prime has to be a plus a for one of the independent sets. But if we don't have too many independent sets and we have more possibilities to choose f double prime, then for at least one choice, this will not be a sum set, and that will give us what we need. Right? So the only thing that's left here is to put all the computations together and to show, okay, but I'll not. So now the last example, but that will have two parts, so that's a longest part. So this is from a recent joint work with Bourgain, and I call it additive patterns in multiplicative subgroups. Okay, so what's the motivation here? The motivation here is what is called sum product theorems. So sums and products of integers, let's say, are something very basic, right? We all think, I mean, in elementary school, we learn to add and multiply integers, and we think we understand it better, but even quite some time after elementary school, at least for some of us, then we realize that we still don't really understand the intricate relation between sums and products, even of integers. And one thing that illustrates it is the following conjecture of Erdős-Szemerédi that is still open. So it says that for every small epsilon, small positive epsilon, if n is big enough and you have a set of n integers, then either you have many sums or you have many products. And many is almost as many as you could have, almost quadratic, namely the number of sums of pairs plus the number of products of pairs is bigger than n to the 2 minus epsilon. So they already proved in the original paper that the number of sums, you see, so somehow maybe the intuition for that is that if a set is an arithmetic progression, then the number of sums is only 2n minus 1, is only linear, that's the minimum that it can be. If it's a geometric progression, the number of products is only 2n minus 1. And this says that in a way, a set cannot be close to an arithmetic progression and a geometric progression together. Okay? And they proved in the original paper some estimate, instead of n to the 2 minus epsilon, they have n to the 1 plus delta for some fixed delta. And this delta has been improved many times. So there is some nice proof by an idea of Seke and Elekesh that connects it to some problem in incidence geometry. And the best known lower estimate is n to the 4/3 up to logarithmic terms. That's due to Scholem-Machine. So still, to know this is still open. But we want to consider, or I want to mention a finite field analog. So that's a result of Bourgain, Katz, and Tau. And that says the following. Here we don't know what is the best dependence of delta as a function of epsilon, but for every fixed epsilon, there is some delta that depends only on epsilon, which is also positive. So that for any prime field, so it's important here to take prime field because we don't want to have subfields. if we take a subset A of this finite field Fp with p elements, then and the size of this thing is still not close to be everything, so it's at most p to the 1 minus epsilon, then the number of sums plus the number of products is at least a to the 1 plus delta. Okay, so again, either we have many sums or we have many products significantly. And we want to consider some extremal case. So what happens if the number of products is the smallest it can be, namely it doesn't grow at all, if the number of products is just the cardinality of A. So that is basically the case that A is a multiplicative subgroup of this prime field, or a coset, but it's the same. So you can assume that it's a multiplicative subgroup. So I'll talk about multiplicative subgroups of finite prime fields a lot, and that's why I want to have this notation. So this will be my notation, that this is a multiplicative subgroup of the finite field. That's right, yeah, because, yeah. So we want here to, that's right, yeah. So this was just some kind of rough motivation, and it's, yeah. I mean, this is not of mine, but maybe I'll still be able to use it sometime during the lecture. We'll see. This is, okay, but I agree. So the sum product was only some rough motivation here, and kind of the most basic question is, suppose we have this multiplicative subgroup of the finite field, when can I be sure that it has one additive relation, at least one additive relation, x plus y equals z? It makes sense to suspect maybe that if the subgroup is big, for example, if it's everything, then it contains an additive relation. And if it's small, for example, if it's only minus 1 and 1, then it does not have such additive relation. So somehow you would expect, and this is what we want to show. So the first thing is a very simple fact. I'll not prove it. And although it's very simple, I think it will be very hard to improve it. For sure, it is not tight. It should not be tight. And it says the following, that if we have a multiplicative subgroup of a finite field, and well, this is true for any finite field, but let's talk about prime field, and its size is at least p to the 3/4, then it is not sum free. There are x, y, z in it, so that x plus y equals z. It's a subgroup, so you can divide by z. Saying x plus y equals z is the same as saying that it has x, y, so that x plus y equals 1. Okay? So this is always true. But the more interesting thing, and I'll tell you something about it, is that there are infinitely many primes p with a multiplicative subgroup of this fp, which is pretty big. And okay. Okay. It's I think everything I'll use will be relatively elementary, so some Galois theory, and but I think it's in a way it's similar to this Konyagian thing. I think, but that's what. Okay. I could, but I could use properties of Gauss sums. Wait, because since you have only 10 more minutes, and you will, but you will see. Yeah, but this thing you will see. This you will see. But okay, but this you will see. So it's not okay. But anyway, so all right. So the claim is that there are infinitely many primes p, and there are multiplicative subgroups that are pretty big. So not p to the 3/4, but p to the 1/3. Again, up to constant, which are sum free, no solution to x plus y equals 1. And I want to tell you something about the proof of this, because I like it. It's kind of nice. So this is more number theories and combinatorics, and it will use a little bit of algebraic number theory, so just some basic Galois theory, and then it will use some facts from analytic number theory, basically about the Linux problem. I'll come. Okay. So let me show you. And both of them are kind of short, but so we just want to construct, right? We want to construct big multiplicative subgroups of prime fields with no solution to x plus y equals 1 or x plus y equals z. Now, before that, I want to tell you the theorem in a more detailed way. So here is a more precise, maybe I'll put all of it. So the more precise statement of the theorem is the following. Let D be any integer. This will be the size of the multiplicative subgroup I'll generate. And it's important that 6 does not divide D. Actually, if 6 divides D, then this does not hold. This is, you could, I mean, if you want to, if I would have wanted this to sound more sophisticated, then I would say that this is, that you could use Mahler's theorem, but really, okay, anyway. So here it is very explicit. 6 does not divide D, because what I say is not true if 6 divides D. Then there is a set E of D. These are the bed primes. So there are not too many primes, D square over log D primes, so that for every prime P which is not in this bed set, okay, and is 1 modulo D, this we need if we just if you just want the multiplicative group to contain a group, a subgroup of size D, then the subgroup of order D, there is a unique one, right, of this FP, it is sum free, okay? Namely, it would have no solution to x plus y equals z or x plus y equals 1. And now what we want to say is that the smallest p, which is not in ED, for which this holds, is relatively small as a function of D, because the size of the group is D. Okay? So if p is like D cubed, then the size of the group is p to the 1/3. So the claim is that for most D, and this is in a well-defined way, so let me not define it, but for most D, p is at most constant D cubed. For every D, p is at most constant D to the 5. And for smooth D, so there is some fixed epsilon, so that if D does not have a prime divisor which is bigger than D to the epsilon, then it's also at most D to the 1. And I'll show you how this goes roughly. So this is okay. So here is a sketch of the proof. As I said, there is part algebraic and part analytic. And so here is the algebraic part. Let's say psi will be a primitive D-th root of unity. And we take we join it to the rationals, and we get the cyclotomic field Q of psi. Right? So we have all these. And then you can check that if 6 does not divide D, then xi to the I plus xi to the j minus 1 is never 0. So that's simple to check. Okay. Now what you do is you define the following quantity. So that's just the product of xi to the I plus xi to the j minus 1 for all ij between 0 and D. It's a product of some D square or so elements. It's all over the complex. I should say, by the way, that you see that here we kind of, it means that over the complex numbers here, if we take psi and all its powers, then we get a multiplicative group, namely of size D, just these powers, and it has no solution to xi to the I plus xi to the j equals 1. But the trouble is that these are complex numbers, and we want to get something modulo p. So the whole effort is to somehow take these complex things and make them to be an example modulo p. So this is what we try to do now. So A will be this product of xi to the I plus xi to the j minus 1. And because this is invariant under Galois conjugation, so if you take xi and map it to xi to the r for r, which is relatively prime to D, then this product stays exactly the same. Then this thing is an integer. So it's an integer, and it's not so big. It's a product of D square things, well, less than D square things, each of them of absolute value less than 3. So it's not too big. And the bed primes, so this E of D will be all the primes, even all the primes which are 1 modulo D, which divide it. So there aren't so many of them, right, because the number is not so big, and they are. And now the claim is that if P is any prime which is 1 modulo D and is not in this exceptional set, then this subgroup D of size D is a good subgroup. And why is this the case? So you see, for every I and j, the norm of xi to the I plus xi to the j minus 1 divides A, because just the product of these with all its conjugates are some of the elements that appear there. Okay? And all these norms, because of this, which are all integers, they are all non-zero modulo p, because p does not divide this thing. Okay? So now we just take G. Deliberately, I'm describing this proof without ever mentioning the word prime ideal. Well, okay, I mentioned it, but I'll not mention it in the proof. So I'll just do it explicitly. So take G in this finite field, P, and let it be an element of order D. Right? And now just map. So think about these integers in this cyclotomic field, but think about the coefficients modulo P, and let us map psi to G. Okay? And I want to extend it to a ring homomorphism. So psi square will be mapped to G square, and psi plus psi square to G plus G square, and so on. And you see that this will be kind of well defined, because indeed xi to the d is 1, and also g to the d is 1. So the way multiplication is here is the same way that multiplication is being done here. And because the above norms are non-zero, the crucial fact is that xi to the I plus xi to the j minus 1 is not mapped to 0, because we can multiply it by its conjugates and get something that is an integer that is not 0, because it's not divisible by p. So there are no 0 divisors in the field. So this is mapped not to 0. And exactly this means that the image of all this xi to the I is indeed a sum-free multiplicative group as we wanted. The only thing that remains to do, I wrote it here, is to estimate the smallest p which is not in E of d. D square over log d primes, yeah. Yeah, definitely, but I want to know that there is a small prime, which is 1 modulo d. Yeah, so this is exactly the Linux problem. So Linux problem is indeed exactly the quantitative version of Dirichlet theorem. You want to estimate the smallest prime, which is a modulo b, where a and b are relatively primes. And the only thing here that here we do not need one prime, we need many primes, because we may have d square over log the exceptional ones, but all the proofs for the Linux problems, they always generate many primes, because they always do it by counting. So, we basically, for 2 of the 3 steps that I wrote there, we use known results, and for the third, we use the known techniques for the Linux problem. You will still get only d cubed, because the bottleneck is somewhere else. You cannot get better than d cubed because of the d square over log d, right? Yeah, yeah. The bottleneck, right? Yeah, yeah. That's right. Yeah, yeah. So it's not. Yeah. Yes. No. But if I use Linux, I'll only get the very high powers that Linux gets. So as I'm saying, if once I go below the cube or something, this is not the bottleneck. But if I'm very high, but it's true that Linux himself. So if I want to stop this problem in the 40s, then I could still get a subgroup of size p to the epsilon for some epsilon, which is very small but fixed. But it's okay. So the estimate for all d follows from some papers of Xyloris, which are basically optimizing the method of 5th round. The estimate for most d follows from the Bombieri-Vinogradov theorem, and the estimate for smooth d, you just have to use the techniques that are used in these papers about the Linux problem. So you have to look at find the right lemmas about the estimates of the Dirichlet functions, and if and Jutila, yeah, this is true, and yeah. Sorry. So Ivanez is Brown, Huxley, Jutila, Gallagher, whatever. Yeah, right. Okay. Okay. So now we can say we can start with the interesting part. Okay. Okay. So that's basically about this. But the only thing I still want to tell you about this problem or this paper with Bourdain is a more combinatorial part of it. And this is when we are interested with more complicated additive relations. So far we looked at multiplicative subgroups, but we only looked at one additive relation, x plus y equals z. Suppose I want some complicated relations. So we started, there was the following conjecture, that a very specific one again, that for every prime p which is bigger than 13, okay, so even for 17, you can always take the quadratic residues modulo p and put them along a cycle so that the sum of every two consecutive ones will also be a quadratic residue. So here's, I wrote how to do it for p equals 17. There are 8 quadratic residues. They are written here. And they are, think about this row as a cycle. So every sum of two consecutive ones, like 8 plus 13, is 21, which is 4, right? And 4 is square, and so on. And, for every, okay. And the question is, was can you do it for every big prime? And indeed, we can do it, but we can do something that is asymptotically much stronger. So suppose you take, you see the quadratic residues are just an example of a multiplicative subgroup, very big, one of size p minus 1 over 2. But suppose we take even one that is much smaller. So the statement is that if we take a multiplicative subgroup of size a little bit more than p to the 3/4, so remember that p to the 3/4 is the best that we know, even if we just want one additive relation. Here we need many, right? Because we need the sum of every two consecutive will also belong. But so if we are just a little bit above that by some logarithmic factors, then indeed there is a cyclic permutation of all the elements of this subgroup, so that the sum of every pair is again in this multiplicative subgroup. And the second theorem, I mean, both of them are somewhat an example of something more general, but so suppose you fix R and you take prime p, which is big as a function of R now, then the claim is that you can take the quadratic residues and put them along a cycle, so that now not only is the sum of every consecutive pair a quadratic residue, but also if you take a pair of distance 2 or distance 3 and distance 4 up to distance R. So if p is big enough, then we can have that all these sums of elements that are not so far along the cycle, they will also all be quadratic residues. Okay. And again, the proof is pretty short, but kind of uses quite a lot. So let me tell you the steps, and this will be okay. So again, it will be it will use the spectral properties of the Cayley Sum Graphs, right? Because this is what we're talking about. And the graph, the specific graph that we look at here, naturally is the group is FP, but think about it as an additive group. And the generating set, or A, is this multiplicative subgroup. But we define it with respect to addition, right? So two elements are adjacent if their sum belongs to A. And what we want is in this graph, if you think about it just in the language of graphs, we want to find a cycle that contains all the elements of the group A. And because it's a cycle in the graph, then it means that the sum of every two consecutive is also in the subgroup, right? Because that's the definition of the edges. Okay, so we want to show it. Okay. And so let me just, to save notation, I call a graph an ND lambda graph if it is a d-regular graph on n vertices, so that the absolute value of every eigenvalue besides the top one is always d, is in absolute value at most lambda. And somehow it is known that such graphs, if lambda is much smaller than d, they have strong quasi-random properties, so they behave like random graphs in some sense. Okay, and here is now a, so I want now to prove this thing, that we are again in FP, we take a multiplicative subgroup that is A, and A is somewhat big, is bigger than p to the 3/4 plus a little bit, plus epsilon, right? So it's okay. So first, I want to look at this Cayley sum graph, FP, with respect to A. So this is a graph, definitely it has P. So remember, ND lambda graph, this is the number of vertices, this is the degree of regularity, and this is a bound for the second eigenvalue in absolute value. So the number of elements is definitely P. These are just all the elements of FP. The degree of regularity is K, the size of A, right? Because it's a Cayley sum graph with respect to a set of size A. And then we can bound all the other eigenvalues. So either we can use some simple properties of Gauss sums, or we can apply veil as it is, and shows that the second eigenvalue in absolute value is at most p to the 1/2. You see that this is useful only if k is bigger than p to the 1/2. Otherwise, it doesn't say anything, but it's OK. So we know that this graph, if k, for our k, which is more than p to the 3/4, looks kind of random. OK. Then we had some old lemma in a paper with Chang, which says that in an ND lambda graph, if lambda is much smaller than d, then every set of vertices, the induced subgraph has the right number of edges, kind of. Okay. So if we look now at the induced subgraph H of this graph on the set A, on the set of elements of the group, right? So because we want to show that this induced subgraph is Hamiltonian. We want to find a cycle that contains, that passes through every vertex of this graph. So this induced subgraph on A, it is regular also. So it is regular just because this is a subgroup. So it's easy to check that because it's a subgroup, it's regular. Every vertex of it has the same degree. And it's regular of the right degree, somehow, of the right degree. And the right degree here, what is it? So the number of vertices is k. And kind of the probability that a pair is an edge is roughly k over p, right? Because k out of the p elements are indeed in our subgroup, in our defining set of relations. So the right degree is k squared over p. And we have the right degree provided this p to the 1/2 is small with respect to k squared over p, which is the case here. Okay. So we know the degree of regularity in this subgroup. Then we know also something about the eigenvalues of this induced subgraph, and it's just by eigenvalue interlacing. This is an induced subgraph of some ND lambda graph. So also all the eigenvalues there, besides the top one, are bounded with the same bounds that we have for the big graph. So we know that this is also a graph in which the second largest eigenvalue in absolute value is only p to the 1/2. Now the degree of regularity is d, which is roughly k squared over p, and the number of vertices now is k. And with our choice of the parameters, k was a bit more than p to the 3/4, so still the degree d, k squared over p, is significantly bigger than p to the 1/2, even in this graph. Okay. And then we just apply a known result of Krivulevich and Sudakov, which says that such graphs, if the second eigenvalue is much smaller with respect to the first, they are Hamiltonian. They have, because so it's maybe expected because they are random looking, and random looking graphs, even if the degree of regularity is pretty small, they are Hamiltonian. So this is something, okay. And then we just realize, this is what I said before, that a Hamilton cycle in this induced subgraph is exactly what we wanted. It's just a circular sequence of all the elements of A, so that the sum of every two is also an element of A. And the second theorem that I mentioned is kind of the same, only the combinatorial result is a bit more sophisticated. It was a result by Ellen, Bocher, Hahn, Koyakawa, and Persson. And they show that, that again, if the second eigenvalue is sufficiently small with respect to the degree of regularity, then we have not only a Hamilton cycle, but a power of a Hamilton cycle, namely a cycle, so that every two that are not too far on the cycle are connected. We can, okay, let me just finish with one open problem on each of the examples I told you. So the first one was this nearly orthogonal vectors, right? So we said that we could have n unit vectors, and among any three, two are orthogonal, and the norm of the sum could be roughly n to the 2/3. It's natural to ask, and again, Lovath asks it in the same paper, what if you know that among any k of them, some pair is orthogonal? Among any 4, among any 5, among any 100. So it can be shown that the sum is at most, I told you then, the upper bound is not so difficult. So, and here too, it's not difficult. So the upper bound is some constant n to the 1 minus 1 over k. About the lower bound, so this is a construction. We don't have this such good graphs here, but there is a different semi-probabilistic argument. It has, but let me just mention that one can show that for every fixed epsilon, if k is big enough as a function of epsilon, then this maximum will be at least n to the 1 minus epsilon. So really, they will all kind of point in the same direction. But the dependence in the upper bound, I think it's something like n to the 1 minus 1 over log k instead of 1 over k. So there is a big gap between the upper and lower bound, and it will be interesting to know if this upper bound is true always or not. Or this is one. Then about some sets, I told you there that I believe that the truth about the maximum number of elements that you can delete from ZP so that what you get is always a sum set should be closer to square root p, I think. So the question is if there exists a set B of size about square root p. I don't care about logarithmic terms here. So that if we omit it from ZP, then what we get is not a sum set. And it will be enough to show that the number of independent sets in a random Cayley sum graph of ZP with respect to a set of size square root p, and it should be true, I think, for a random set of size roughly square root p, that the number of independent sets is roughly p, is not more than p to the square root p with high probability, or that the biggest independent set is not much bigger than size square root p, is essentially the same, should be true. Again, I don't know. This would be nice. And then about these sum-free subgroups, and of course, we had a big gap between the upper bound. So we asked how big should a subgroup be so that we can get one additive relation. Forget even the more complicated structure, just one additive relation. So it's between p to the 3/4 and p to the 1/3. And the question is if p to the 2/3, so I wrote here, p to the 2/3 should be enough if we assume some common conjectures in number theory. So something about square root n cancellations in multiplicative subgroups. So there are some conjectures of Montgomery and Vaughan and Woolley, and they would give p to the 2/3. So this should be true for any field, I think. Again, it's not, we don't know to prove it. And also the p to the 1/3. It doesn't seem that this is tight. So there are two different heuristics, and both of them are reasonably convincing. And one of them tells you that the truth should be p to the 2/3. I should say that for fields of characteristic 2, the truth is indeed p to the 2/3. So these are things that are called cyclic caps in finite projective spaces. So there are some constructions for non-prime fields, but prime fields seem to behave very differently. And there is another heuristic that suggests that the truth should be p to the 1/2, but both the upper and the lower bounds are neither of these. So again, it will be interesting, and it will require new ideas, both to improve the upper bound and to improve the lower bound. And with this, I'll finish. Thank you.